Hello everyone and welcome back. Today I am going to start a new topic which will be on radiographic testing. So, like what we do always, first we will see the basic principle of this and then we will go on to see the technique how it is done. So, radiography, as you all know, is based on, or it is done by using X-ray radiation. So, before we go on to the basic principle, let us first learn a little bit about the properties and nature of X-rays, and then we will see how the X-rays in this case are used for doing NDT or radiography. To start with, I first want to show you this. I am sure you all have seen this at some point or the other. This is the electromagnetic spectrum, which is also simply known as spectrum, where you can see the wavelength and frequency of different types of electromagnetic radiations, including visible light and X-rays. Okay. So, here you can see when you talk about the wavelength, it decreases going towards right and increases towards left. Okay. So, as you decrease the wavelength, the energy in the electromagnetic radiation will increase, because the relationship between the energy E and the wavelength or frequency is given by this. Wherein H is Planck's constant, nu is the frequency, lambda is wavelength, and c is speed of light. Okay, so, as you increase the frequency or decrease the wavelength, the energy increases. Okay. And you can see the X-rays towards extreme end in the range of 10 to the power minus 8 to 10 to the power minus 10 meter. This is the range of wavelengths for the X-ray radiation, which is much lower compared to visible light, which is in the range of 10 to the power minus 7, okay, which will be around this region. So, this tells you that the X-ray radiation is much more powerful compared to the visible light, and that is why X-rays can penetrate through materials, okay, because the energy level in X-ray radiation is much higher compared to what you have in any other electromagnetic radiation. So, when you have X-rays in the range of 10 to the power minus 8 to 10 to the power minus 9 meters in this wavelength, these are known as soft X-rays. And if you increase the energy further, that means if you decrease the wavelength to the range of 10 to the power minus 9 to 10 to the power minus 10, then in this case the energy of the X-rays will be much higher, and these are known as hard X-rays. Okay. And if you further increase the energy, and if it is less than 10 to the power minus 10 meter, then this will fall in the gamma rays radiation range. Okay. So, this was about the energy which depends on the frequency or the wavelength, and due to this very small wavelength, X-rays have very high energy, and as I said, that is why they can penetrate through matter. Now, if you talk about the nature or properties of X-rays, these are the typical characteristics of X-rays. They cannot be detected by human senses, you cannot see them, you cannot feel them, by any of the organs you cannot detect them. Then they travel in straight line with the speed of light, and their path cannot be changed by electrical or magnetic field. But they can be diffracted to a small degree at interfaces. Between two materials. And the other properties are they can pass through matter, as I told, because of the high energy levels. And this degree of penetration will depend on their energy and the material that they are going through. Okay, so every material will interact with the X-rays, and the level of penetration will depend on the material properties, which we are going to talk about little later. And X-rays have enough energy to ionize matter, and can damage or destroy living cells. That is why they are dangerous to human beings. You cannot really expose yourself just like that to X-ray radiation. You need shielding and all that. And when medical radiation is done for medical radiography, in those cases the energy level in the X-rays is much lower. But even then you have seen precautions are given that you are exposed to X-ray radiation. Okay. So, these are the typical properties of X-rays, and now that we are going to use X-rays to do radiographic testing, we should also know a little bit about how these X-rays are generated, because in the radiographic machine also you have a X-ray generator which generates the X-rays which are then used to do radiographic testing. Okay. So, let us see what is the kind of equipment which can be used to generate X-rays. So, the basic principle behind generation of X-rays is that X-rays are generated by acceleration and then deceleration of electrons. So, first you provide high velocity to electrons, and then when you decelerate them, this kinetic energy which was provided to the electrons will be converted to X-ray radiation. That is the basic principle behind this. So, that means you need a source of electrons first, and then you need to accelerate them to very high velocities, and when you stop them on the other end, then this kinetic energy which is provided to the electrons will be converted to X-rays. Okay. So, that means you need two things, one is to generate the electrons and the other is to stop the electrons. Okay. So, in order to generate electrons, you need a material which can easily emit electrons when you provide a bias. Okay. So, tungsten is one such material which can be used for that purpose, and tungsten filament is what is used as the electron emitter or the electron source in this case. The symbol for tungsten is W, and when you stop it, that is on the other side of this instrument, which is basically a tube, you have another material which stops them. So, that is called the target. So, here on the target the electrons will come and impact at high velocities, and due to that lot of heat will be generated, right, and that is why the target should be made of a material which has very high melting point. Okay. So, that means in this case if you want to use a metal, you have to use those metals which have very high melting point, and these kind of metals are known as refractory metals because of their high melting points, and molybdenum is one of them which has very high melting point. So, this molybdenum is used as a target on the other side of the tube, on which these electrons will impinge at high velocities, and their kinetic energy will now be converted into X-rays. So, in order to provide the kinetic energy to the electrons, you need to maintain a very high voltage between this tungsten filament and the target. So, the tungsten filament is the cathode and the target, which is the molybdenum in this case, is the anode. Okay. So, you need to first generate these electrons from the tungsten filament by providing a bias to it, and once the electrons are emitted, you need to accelerate them towards the anode by maintaining a very high voltage difference between the anode and the cathode. Okay. And for the electrons to move from the cathode to the anode, you need to create a vacuum between the anode and the cathode. Okay. So, that means this whole thing has to be done inside a tube, and this tube has to be maintained under vacuum. Okay. So, in one side you have the tungsten filament, and on the other side you have the target, and you keep them inside a tube which is evacuated and kept under vacuum. Okay. Now, if you maintain a voltage difference to the tune of 30 to 50 kilovolt, between the anode and the cathode, then these electrons will be accelerated at high velocities towards the anode. Okay. And when they are stopped at the anode, they will be decelerated. So, they are stopped at the anode. So, this kinetic energy which was there in the electrons will now be converted into some other form of energy. Most of it will be converted into heat energy, and that is why this anode, in spite of it being a high melting material, it has to be water cooled, because as I said, most of the energy in the electrons will be converted into heat, and a small fraction of it will be converted into X-rays. Okay. Right. So, this is how X-rays are generated. So, this is basically an X-ray tube which is maintained in vacuum, and the main components of this tube are these two electrodes, the tungsten filament cathode and the molybdenum anode, and then you have to maintain this high bias between the anode and cathode, and then you can generate these X-rays by this energy conversion. So, now that we have understood little bit about X-rays and their properties, so now it is time to talk about how these X-rays are used to do radiography testing. Okay. So, in order to explain the basic principle behind radiographic testing, I would like to first show you this picture. Okay, so I like to use this picture to explain the basic principle behind radiographic testing. I believe you all have seen this picture at some point in time in your life, if not for your own body parts, maybe for somebody else's, but you all have seen this, right. So, this is a medical radiograph of our hand, and you can see the bones clearly. Okay. So, this is how when you expose our hand to X-ray radiations, this is how the image would look like. Okay. The question that I want to ask you here is that the bones that you see, they always appear white compared to the rest of the portion of the body. Okay. Have you ever wondered as to why these bones always appear white on a radiograph? The basic principle behind this technique lies in the answer to this particular question, okay, as to why the bones always appear white on a radiograph. Okay. So, let me explain that, and that will give you the basic principle behind this particular technique. This goes back to a property of any substance called absorption. Okay. So, whenever X-rays pass through a matter, there will be some kind of interaction between the X-rays and the matter, and as a result of that, some amount of X-ray energy will be absorbed by that material. Okay. And this absorption ability varies from material to material, okay, and it will depend on some of the material properties, and density being the one of the most important properties on which this absorption will depend on. Now, if you look at our body parts, bones are the most dense in human body. Okay. So, when the X-rays pass through the bones, or when the X-rays pass through human body, bones are the areas where the absorption of the X-rays will be much higher compared to any other portion of our body. Okay. So, what happens when you do radiography? You have a X-ray source, okay. Then you put the body parts or the sample that you want to radiograph, and then after that, in contact with the sample, a radiographic film is kept on which the image is captured. Okay. Now, this radiographic film is made of a material which darkens on exposure to any electromagnetic radiation, including visible light. Okay. So, this is nothing but the photographic film or the negatives that you would have seen, which were used before to take photographs. Before the before the digital radiography came into picture, people used to use this photographic film that we have seen as negatives. Okay. So, this is a very similar thing which is used in case of X-ray radiography also. You expose the sample to X-rays and capture the image on the photographic film. Now, as I said, the property of the photographic film is to darken when it is exposed to visible light or X-ray radiation. Okay. So, this X-ray film or the radiographic film that you have, this is primarily made of a silver halide emulsion. Like silver bromide can be used for that purpose. So, this emulsion is coated on a thin plastic sheet, and that is what you see this film as, a thin plastic sheet, which most of the time appears dark to us, because by the time we see it, it is already darkened. And the reason why it darkens is this silver bromide particles that you have. Okay. So, this silver halide or this silver bromide is a material which can easily interact with X-rays, and when they interact with X-rays, some of the X-ray energy will be absorbed by this material, and due to that the bond between silver and bromine will be broken and silver ions will be liberated. Okay. So, that is what happens when X-ray intensity falls on this film. And it liberates the silver ions. Okay. So, this liberated silver ions are the main responsible factor for the contrast or the darkening that you see on the X-ray film. Okay. And this extent of darkening will depend on how much radiation or how much energy is falling on the film. Okay. If the energy falling on the film is high, then the extent of darkening will be high, and vice versa. Okay. So, that means this will depend on how much energy is being absorbed by the sample on a particular part. Okay. So, in this case, in this particular radiograph, since the bones are the most dense parts, they will absorb more energy compared to the flesh and the tissues around it, and that is why the energy coming out from the bones will be much lower compared to energy coming out from other portions of the hand or any other body part, and that is why these bones will appear white, because the energy coming out from the bones is lower, and when it falls on the radiographic film, the extent of darkening as a result will be lower compared to any other portion of our body part. Okay. And that is why, owing to their high density, these bones will appear white on a radiographic image. Okay. So, that is all fine, but how do you define it? I mean, do you have any expression or something that can describe this particular phenomena? And yes, we do have an expression through which we can describe this mathematically, and that will give us little more understanding as to why this happens, and that will help us in turn in understanding the basic principle behind this particular technique. Okay. So, let us talk about that particular expression or the equation, which is the basis for radiographic testing. Okay. And you can get an expression like this. Which in fact can be derived based upon the absorption of X-rays when it travels through a particular material of thickness x. That is what you see over here. So, it will depend on the thickness of the material. That is one factor which will control the intensity I which comes out from the material after traveling through this particular distance x, and I naught in this case is the initial intensity. So, the initial intensity falls on the material, and then it goes through the thickness of the material, and this is the decrease that you see I by I naught, and this decrease is exponential with respect to the distance that the X-rays travel. And one more parameter that you could see here, which is mu. So, this is a material property which indicates that the extent of absorption will depend on the material through which the X-rays are traveling, and this particular parameter is known as the linear absorption coefficient, which is different for different materials. Okay. So, this we are going to take up in more detail in the next class. We will take it up in the next class, and we will discuss about it and then see how that can be used to form the basis of radiography testing. So, for today this is all I have. I am going to stop here today, and I will see you next time. Thank you for your attention.